Let's start the study of black box search with optimization problems, like the traveling salesman problem, for instance, or the quadratic assignment problem. So an optimization problem is a problem with an objective function that you try to optimize, to maximize or minimize. And as you know, it's very important for optimization problem where we use branch and bound techniques like in constraint programming. It's very important to discover quickly very good solutions, because if you are able to find quickly good solutions, then the pruning induced by the bounds, the upper bound that you have found, will be much stronger. So it's quite useful to discover quickly good solutions. And the way to implement, to discover a good solution is to have a good value heuristic. The value heuristic is very important for optimization problems. And usually for an optimization problem, you can easily come with some heuristic. For instance, if you take the traveling salesman problem, you might say, I want to pick as the leftmost value the successor variable that is the closest city according to the city that you try to instantiate for the traveling salesman problem. And so this is exactly the idea that we would like to have here. We would like to follow on the leftmost branch some strategy that would be quite similar to what you would follow with a greedy algorithm. So let's take, for instance, a TSP. So for a TSP, you have some cities, right? And the variable represents a city. And given that you pick this variable next, the next successor that you will take is probably the closest one. So you may take, for instance, this one, okay, on the leftmost one. And then after this one, you will probably go there, right? And then you would go there, and then you would go there, somewhere here, and then here. We would like that this solution that I just have shown correspond to the leftmost branch of the search tree. The goal now is to automate completely this kind of strategy that we just have seen for the traveling salesman problem. How to make this automated. Okay, so again, for the TSP, this is exactly what you would do. You would like to pick up successor value as a successor value, the closest city according to the next one. Okay, and eventually you find this solution that corresponds to the one that you would discover with a greedy strategy. So a branching, if you remember, is a two-step choice. First, you have the variable choice, and then you have the value choice. Okay, and the value choice that we will implement here comes from this paper, and this paper is entitled "Making the First Solution Looks Good." So by looking good, we mean look exactly like you would discover this solution with a greedy heuristic. Okay, and the intuition behind this paper, this idea is that we will select the value with the lowest objective lower bound after the propagation of the assignment to this value in a minimization problem. So the idea is this one. You have the variable x that you want to instantiate, and then you will try some value on the left, okay? By deciding this value on the left, you will increase the lower bound on the objective function, okay? And if you take another value, for instance, rather than v, you take v prime, maybe you will lower the lower bound a little bit more. And you would like to choose the value that will lower the objective lower bound. And this is formalized here with the pseudocode on how to implement this. So we want to minimize this objective function subject to some constraint. And we want to design the value heuristic according, once we have chosen already the variable, let's say x3. Which value should we decide? Should we decide v1, v2, v3, or v4? That's the question that we want to solve here. And we want to make the first solution look good, so we want to take the most promising value on the left. So the idea is simply remember the best solution, the best increase, and the best objective here. Then you will try successively each of the values of the domain. You will store the state according to the state manager. So you remember the state so that you can undo the state of the solver. Then you try for the variable x3, you try the value v, which is the next one. You try the value v. If the lower bound has increased less than what you had before, you say that V is probably the best candidate to be chosen on the left because it has a lowest impact on the objective function if you take that one. And this exactly corresponds to the greedy heuristic, right? If you remember the TSP, you have the choice between this successor and this successor for the TSP. If you take this successor, you will increase by this distance the lower bound, and if you take that one, you will increase the lower bound by d prime, which is larger, okay? And so you will prefer to branch first on this one, which is the closest successor. And this is exactly what we are doing here, okay? We will take the value v if the impact on the lower bound, this is the impact of the, this is the impact on the lower bound. We ask to the minimum of the objective variable, okay? If the impact on the lower bound of the objective variable is less than what you had found so far, you will say that the value v is the next one what we should branch on. And then, of course, you restore the state. Just after having tried the value v, you restore the state, so that the next time you try the next value, you start again in the same state as before. And then once you have found the best value, best here, you will branch on that one on the left, and you remove the alternative, the corresponding value on the right. So this procedure is quite costly because you will really do the propagation and the fixed point computation, right? This is doing the fixed point computation, okay? When you do this line, when you execute this line, you compute the fixed point. And this is why it's quite costly to do it at every node of the search. And so to make the usage of this very nice and elegant ID a little bit cheaper, we advise you to use this strategy only to discover the first leftmost solution, and then you can deactivate and use a fallback heuristic that is that is faster to use. So we advise you to use it only for discovering the leftmost solution, which is that one. Okay. Once you have discovered this solution, for the rest of the search tree, you use another strategy that is a little bit faster. But discovering this first solution, which should be very good quickly, might be done by using this idea.